So we're starting derivatives. Derivatives are basically half of what this class is. Okay, so calculus, there are two parts of calculus. There's differential calculus, there's integral calculus. Okay, so before we could get into derivatives, we needed to go through limits. Now that we're basically done with limits, we're going to start derivatives. Okay, so derivatives. What is a derivative? Okay. So what is a derivative? So in chapter 2, we're going to define the slope at every curve at the point where x equals a to be the limit as h goes to 0. This should look familiar. This is a difference quotient of f of a plus h minus f of a over h. When it exists, this limit is called the derivative of f at a. Now we're going to look at these derivatives and we're going to be using them as slope. Okay? So the derivative of a function with respect to the variable x is the function f prime. Okay? So f with that little apostrophe mark, that's what we deal with when we talk about f prime. And that value of x is this. So provided the limit exists, and that's one of the things that we always have to check, and I did that to you guys last week, where I asked you to find the slope at an asymptote, where the limit does not exist, and you will not be able to do that. So as long as this limit exists, we start calling it the derivative. Okay? This right here is what we call the definition of the derivative. All right? So the limit as x goes to 0 of f of a plus h minus f of a is also called the derivative of f of a. Okay? We write it as f prime of x. So this is what we call the derivative of f. Okay? So just like, so when we start talking about this derivative, okay, there's a lot of notation that goes along with it. Okay? So first thing we're going to do is we're going to talk about that. Okay, there are many ways to write the derivative of y. So this is f prime. Okay, and this is the part of your notes where actually I told you to leave part of it blank. Okay, because all of this is not going to be there. So this is f prime of x. That's how we say it. This is or the derivative of f with respect to x. Okay, so these are both ways of saying this. F prime of x or the derivative of f with respect to x. This is y prime. So there are going to be times if I give you y and you take the derivative, you get y prime. If I give you f of x and you take the derivative, you get f prime. So we have it in different situations. You guys have to know this notation. So when you see y prime, you know it's the derivative of y. Okay? Now, dy over dx. Okay? And that is said dy over dx. Okay? Or we could also say the derivative of y with respect to x. Okay? So now, we have two ways of saying the derivative of y. We have y prime and we have dy over dx. Okay? Which literally stands for change in y over change in x. It's not delta y over delta x. It's not the triangle, but it's a derivative of y. So we think of dy as a small change in y and dx being a small change in x. Okay, so it's like slope almost. All right. Now the next one we use is df over dx, which you can imagine. df dx. Or again, the derivative of f with respect to x. So now you've got two ways of doing f of x. You get two ways of doing y. And I'll just throw them in there so you guys are going to have to know. Okay? So I will change it all the time. As a matter of fact, sometimes I use T or M or N. Doesn't matter. Okay? We'll go over notation more. And the last one that we use more than anything is this one. This is basically telling you d over dx. It says take the derivative of my function f of x. And of course, we say this one, d dx of f of x. But again, this is just the derivative of f with respect to x. All right, so these are just a few ways that we use to notate the derivative. Okay. Now, you can already see that this is going to get a little bit crazy. Now, a function is differentiable if it has a derivative everywhere in its domain. It must be continuous and smooth. Function on closed intervals must have one-sided derivatives defined at the endpoints. Okay, so differentiability, huge. Okay, when I say a function is differentiable, automatically you should know that that function is therefore smooth and continuous. Also, if they tell you that a function is smooth and continuous, you should automatically know that that function is differentiable. You have to know it both ways. The AP test loves to put on there that word. Okay. Matter of fact, the one that I showed you guys with the slope, literally says it has twice differentiable function, which means the first derivative and the second derivative are differentiable, which means it's telling you that both of them are continuous and smooth. And yes, we'll be taking multiple derivatives sometimes. I think 3 years ago there was a question that asked you for the 26th derivative of a function. Okay, which means you have to take the derivative 26 times. Okay, but there's a trick to it. All right, so this is definitely one of those things that you should have written down on your note card. Okay, now the derivative at a point. This is another equation that you need to know. The derivative of a function at f at the point x equals a is this limit. So this should also look familiar. What does it look? What does it look like? All right, so here we go. Dx does not mean d times x. Dy does not mean d times y. Okay? Dy over dx does not mean dy divided by dx. Okay? Except when it's convenient to do so. And I will let you know when that will happen. Okay? But for right now, it is not like a fraction. It means the derivative of y with respect to x. df does not mean df divided by dx until it's convenient to do so. And I will let you know when that occurs. Okay? We are not solving equations yet. Okay? When we get into those, then we'll start doing that. And of course, this also does not mean the same thing. Okay? It'll make sense later. Okay? All right, so let's get into some of the more necessary information. Okay? This chart right here, you need to know it backwards and forwards. Okay, this is one of the most used charts that we're going to use. We're going to add another layer to it eventually. Okay, when we start talking about second derivatives. But let's talk about this a little bit. So, if my graph of f is increasing, what does increasing function look like? Yeah, as we move from left to right, the y value starts to go up. Okay? That means the graph of f prime is positive. Okay? So we're now relating the graph of my original function with the graph of my derivative. But what is the derivative? It's a slope, right? So look, when you have a function that's increasing like this, the slope is positive. For those of you guys that are in physics or have taken physics, this should sound familiar. They tell you that when the function is increasing, the slope is positive, and when the function is decreasing, the slope is negative. Right here. If my function is decreasing, and they use velocity, right? When they talk about velocity versus position? Yeah. And that's because position is my graph and velocity is the slope of that graph. And basically that means if position is my function, f of x, that means the derivative is velocity. And actually the derivative of velocity is acceleration, and we'll get into that later. Okay, it all relates. So when my function here is decreasing like this, my slope is negative. So I'm going to draw a tangent in here. And you can see the tangent right there is negative. Just like if I drew a tangent here, the slope of that line is positive. When you have a maximum or minimum value, what does that look like? Either like this, maximum, or a minimum. At that maximum or minimum point, the slope is 0 because we have what's called a horizontal tangent, like that. And the slope of a horizontal line is 0. This is going to become really, really, really important. Okay? All right. Any questions on this? This is something you're just going to have to know. Okay? There are many times on a quiz where I'm going to actually ask you to write down this chart from memory. Okay? All right. So, basically we're going to go over this concept. So, I've given you this graph. Looks like this. Okay? This is my f of x. So what we're going to do is the derivative is the slope of my original function. So I'm going to graph the derivative. So this is the graph of the derivative. So if I look at here, between 0 and 1, what is the slope of this curve? Well, from 0 to 1, my rise is 2, my run is 1. So what's the slope there? 2. So when I go to draw my derivative, the slope from 0 to 1 is 2. Like that. Then I look from 1 to 4. What's the slope from 1 to 4? Well, my rise is 1, and my run is 1, 2, 3. So it's 1/3. The slope, the run is 3. Starting from here, rise is 1, run is only 1, 2, 3. We end up at 4, but this is 1, 2, 3. Okay? All right. Now, the next one. From 4 to 6, we have slope of 0 because it is a horizontal line. So you can see right here, from 4 to 6, I'm at 0. And then from 6 to 9, my rise is -3, my run is 3, which means my slope is -1. Now, notice when I started, I had an endpoint, I had a closed circle, right? But notice right here at 1, I have open circles. And right here at 4, I have open circles, which means the derivative, there is no derivative there, right? And same thing at 6. Why is there no derivative there at those places? At 1, 4, and 6. No, it doesn't have anything to do with the left-hand and right-hand limit because the left-hand and right-hand limit exists there. The limit does exist there. Why is there no derivative at 1, 4, and 6? Nope. You already forgot what I just told you. Because it's not smooth. A function only has a derivative where it is smooth and continuous. Is this smooth right here? Is that smooth right there? What about that? Is that smooth? No, that's a point, a short corner. So the derivative there does not exist. The derivative is a limit as well. So anywhere where the slope does not meet at the exact same place, there's also no derivative there. So Kelvin, you were kind of right, but not. It's not if the function meets there, is if the slopes are the same from the left and the right. That's not what you said. All right. So look at this one. Okay. This should look familiar. Okay. So I'm going to use my definition of the derivative to find y prime. So notice I started with y, and now I'm taking the derivative, and I ended up with y prime. So I took the derivative of this side to find the slope. I'm using my slope equation. So this is my f of x plus h minus f of x. Okay, so has anything changed since we were doing the difference quotient? No. Okay, so we're doing the exact same thing we've been doing. So next step, FOIL this out. The 3 and the positive 3, 0 out. X squared minus x squared. And look, again, I should have just h's in the top, right? Everything better have an h. Those h divide out. So we get the limit of 2x plus h. We plug in 0 for h. And look what we get. Y prime is 2x. We've already know this, right? Before it was, when it was a plus h, it was 2a. Now it's 2x. So the graph, or if I graph 2x, that's the graph. Okay, now let's look at what we've been talking about. Remember that chart that I just told you guys about? How the function and its derivative relate? So look, right here, on this side, on the negative side of the parabola, what is my function doing? It's decreasing, right? Look right here, on the left side of 0 of my derivative. Where is it at? Not decreasing, it's negative. When the derivative is negative, my function is decreasing. Where my function is increasing, my derivative is positive. These represent the slopes. So for instance, if I look at 1 right here, if I look at my derivative, 1, x is 1, y is 2. Because the slope at 1 is 2. How many times have we done that with this function, x squared? Too many, yes. Okay, but this graph represents the slopes. This is the graph of my derivative, which are the slopes of my graph. So if I want to find the slope at 3, what's the slope at 3? 6. So if I go right here to my graph, I know that this slope right here, the tangent line, is going to be a slope of 6. And look, the slope right here says it's 0, and that's that horizontal tangent right there. Okay? So you have to be able to read this. Eventually, you're going to have this, the original graph, f of x, and you're going to have to graph this without doing the actual derivative. I'm not going to give you the actual equation. You can't do the equation this way. You're going to have to just graph it from this graph. It's actually easier than it sounds. Okay? Promise. All right? Nope. For reals. All right. Any questions on this? Now, I put this in the notes twice because it is so important. A function is differentiable where it has a derivative everywhere, and it has a derivative if it is continuous and smooth. Okay? Super important. All right? That's the basics for derivatives.